Hello, and welcome to Monthly Mailbag, where we answer science questions that you, our wonderful audience, send in. Sometimes we tackle the mysteries of the universe, and sometimes we talk about blind birds, but this time, we're sticking a little bit closer to home. I've been particularly excited for this episode because it combines some of my favorite things: physics, mysteries, and showers. This month, we're answering Twitter follower David's question: why does the shower curtain billow inwards when you turn on the shower? It's a great question, David. For those lucky enough to have glass showers who may be unfamiliar with this effect, let's take a little field trip. Welcome to my shower. The phenomenon is pretty simple. You turn on the shower, and then the shower curtain kind of attacks you. Let's see it in action. Some nice billowing there. So it works best with a powerful stream pointed downwards. The simplest explanation is that there's a chimney effect going on. That the hot air from the shower is rising up over the top of the curtain, and the cold air in the rest of the room is sort of coming in from the bottom, pushing this curtain inwards. But that can't be right, because the water behind me is actually cold water. It's how we can get such a powerful stream, by turning both the hot and cold on full blast. The next explanation is that it's because of something called the Bernoulli Principle, which states that fast-moving fluids, liquids or gases, have lower pressure than slow-moving ones. When a fluid speeds up, its pressure lowers. The fast-moving water coming out of the shower head pulls the air around it, making it move quickly as well. This fast air has low pressure, which sucks the shower curtain in like a vacuum. Bernoulli definitely has something to do with it, but it's not the whole picture. If it was a simple Bernoulli situation, you'd expect the curtain to get pulled in all along the length of the water flow. But it doesn't. It's only the bottom that billows. In 2001, an American engineer named Dr Schmidt wanted to get to the bottom of it. So he enlisted the help of some software. He simulated a simplified scenario, without heat, without evaporation, or a person in the shower. And he found something surprising. A vortex formed above the spray. The center of the vortex, much like the eye of a storm, has lower pressure than the rest of the shower. And it's this vertical vortex that's responsible for the billowing. Dr. Schmidt won the Ig Nobel Prize, an award given for achievements that at first make people laugh and then make people think, for this partial solution in 2001. But that's nearly 17 years ago now, and I figured computer simulations have come a long way since then. So I enlisted the help of engineer Dr. Dominic Flynn at Birmingham City University. He drew up a model of the shower in CAD, and he fired up the modern version of the software used by Dr. Schmidt in 2001. And he ran some simulations. You can see this little animation here. The see-through box is the shower area. The solid-colored curtain is the shower curtain. The water is coming from the circle in the top right. Warmer colors represent higher water speeds, and the colors in the shower curtain represent displacement, how far the shower curtain is moved. So let's play the simulation. And we can play it again, and you can see the movement at the bottom there. So we found the same results. Maybe it's helpful now if you look at the cross-section. It's not the most stable situation in the world, but you can see there's definitely a circular vortex forming. One big difference between Dominic's simulations and Dr. Schmidt's simulations is that Dominic's vortices were quite a bit lower. But our shower head was also pointed straight down in this simulation. Our simulation is a little bit more complete. It has heat, but still no person or evaporation. So we're still one step closer, but we can't say we have a full solution. So let's return to David's question. Why does the shower curtain billow inwards when you turn on the shower? Shower curtains billow inwards because of Bernoulli's principle, but not in a straightforward way. The fast-moving air of a swirling vortex has low pressure, which pulls the curtain inwards. The bottom of the curtain is the part that moves because of another key principle of engineering, the principle of moments. The part of a lever that moves the most with a given force is the part furthest from the pivot point. And the pivot here is the curtain rod way up at the top. Although it is a flexible material, so it gets a bit more complicated than that. Now that we know what's going on, here are a few tips that can interfere with the effect. The pull isn't very strong, so you can make the shower curtain harder to move by sewing magnets or weights into the bottom. Or you can get a curtain made out of a heavier material. A curved curtain rod can also interfere with the effect by encouraging the bottom of the curtain to stick to the tub. This episode wouldn't have been possible without the generous time and effort given by Dominic Flynn, a fantastic engineer who helped us out with these lovely simulations. I also want to give a shout out to Dr. David Schmidt, who kindly answered what must have been the millionth email about a silly project he did almost 2 decades ago. And this was actually my last episode of Monthly Mailbag. I'll be leaving the RI and headed back to Canada, so I have a few other special shouts out to do before I go. I'd like to thank Cassie, Lena, and Ed, who decided it was a good idea to put me in front of the camera, to Ant for taking these videos to the next level, and to Sarah and Anand for letting me run with it. And really to the whole RI team for being so supportive. And finally, thanks to you, the viewers and subscribers. You make all of this possible and worthwhile. If you want to keep in touch, I'm on Twitter @PharaohJohn. See you around. That reminds me, I think I left the shower on at home.